Okay, welcome Vorotnikova, and she's going to tell us about streaming algorithms for matchings in low arboricity graphs.
All right, so hello everyone. Today I'm going to talk about graph streams and approximating the size of maximum matching in low arboricity graphs. This is joint work with Andrew McGregor. So I'm going to start with talking about the streaming model and why we might want to use it. And I'm going to use social networks as an example throughout my talk. So let's say we want to represent a social network as a graph and then solve some problem on that graph. So then users of the networks would correspond to vertices and their friendships to the edges. And if you go to someone's page and look at their friends list, then what you're getting is basically a list of edges which are incident to a particular vertex in the graph. However, social networks are not static because people can friend and unfriend each other, which would correspond to the edges of the underlying graph being added and deleted. And note that now those updates are no longer grouped by user or vertex. They just come in some arbitrary order. And we can also consider a slightly simpler model where we can only add friends but not delete them, because if you unfriend someone, they will be very offended. And in this model, the updates still come in an arbitrary order, but we're only adding edges to the graph. So let's see how that is related to the streaming model. In streaming, we're assuming that we know the vertices of the graph in advance, though for some algorithms, we don't need that assumption. We start with an empty graph with no edges, and then observe a sequence of edge updates. And we can only look at the sequence once, so we're saying that we're taking one pass over the stream. So these are the three streaming models that I'll be talking about today. The most general one is dynamic streaming, where updates come in arbitrary order, and we can both insert and delete edges in the graph. Now, in insert-only model, the order is still arbitrary. However, we can only insert edges, but not delete them. And then finally, in adjacency list streams, we're only inserting edges. And now edges incident to the same vertex arrive together in the stream. And actually, we're going to see every edge twice, once for each of its endpoints. So we want to compute some function of this graph that is defined by our stream. The problems considered are such as maximum matching, determining whether the graph is connected, counting the number of triangles, and so on. And our main objective is to minimize the amount of space that our algorithm is using, because we're assuming that the graph that we're dealing with is really large, and in particular, we cannot store all of it. Fast update time is also generally encouraged, but on the other hand, we're assuming that we're only extracting the solution once at the very end of the stream, so the post-processing time can be quite large. So why do we want to use this model? First, as I mentioned, we're assuming that the graph is really large, so it doesn't fit into main memory. And then if we're reading it from some sort of external memory device, then this sequential reading can be faster than random access. The graph can also be distributed across multiple machines, in which case our edge-by-edge approach is just an extreme case of batch-by-batch. And finally, the graph can be changing over time. And streaming allows us to store and update just the summary of the data as opposed to the entire data set. So in general, we want our model to be quite restricted. But on the other hand, we want to solve general graph theoretic problems. In this way, we come up with techniques that extend to other models and also can be used in a variety of applications. So the main thing that can be done in graph streams is sampling. We can sample edges uniformly, non-uniformly. We can also sample vertices and then collect incident edges on them. Other things that can be done easily are computing the degrees of vertices or some other quantities that depend on the degrees. And finally, some algorithms also take the ordering of the stream into account. So let me just quickly go over of how we can sample edges. So assume we just want to sample one random edge from uniformly at random from the set of all edges in the graph. If the stream only has insertions, then it can be easily done by reservoir sampling, where we're keeping the first edge in the stream. And then for each ith edge, we replace the edge that we're currently storing with this E sub I with probability 1 over I. And then at the end of the stream, we have a random edge. If the stream has both insertions and deletions, sampling a random edge is not quite as intuitive. We have to use what is called L0 sampling, where such a sampler returns random edge, fails with probability delta, and it uses space roughly log squared n times log delta to the -1. So we can make this failure probability as small as we want at the expense of a slight increase in space of the algorithm. And I'm not going to go into the detail of how L0 sampling works. We're just going to use it as a black box. And finally, if we need to sample a set of vertices, we can use a hash function to do that. So we can do it on the fly, as opposed to pre-sampling in the beginning of the algorithm and storing all that information.
So the failure here refers to the edge that is sampled by L0 sampling may not be a random sample, or it just...
So it might not even return an edge that is a valid edge of the graph. OK, so the particular graph problem that I'll be talking about today is maximum matching. And let's go back to our example of a social network. Imagine that your computer science department is organizing an event, and each grad student is allowed to bring a +1. But since they're grad students, they don't have friends outside of the department. And what they want to do is basically to pair up among each other. And this is an example of such pairing. So the students who are paired up are happy, and the rest of them are very sad and lonely. So we want to minimize the number of unhappy students by maximizing the number of pairs. And then the list of pairs is then called the matching in this graph. So defined more formally, a matching is a set of edges of the graph that don't share any endpoints. And we want to find such a set of maximum size. So in this graph, for example, the two green edges form a matching, and it is a maximum matching in this graph. So if our stream only has insertions, then we can just run the greedy algorithm to obtain a maximal matching, which immediately gives us a true approximation of maximum matching. However, a matching can be as large as n over 2, so that algorithm uses linear space in the number of vertices.
What's the difference between those two terms? Maximum.
Maximal means that we cannot add more edges to the matching, and maximum means of maximum size. And those can be a factor of 2 away from each other. So if we want to do better than linear space, then what we can do is, instead of finding the edges of the matching itself, we can just try to approximate the size of it. And in some cases, that gives us sublinear space. In particular, I will be concentrating on the class of graphs of arboricity alpha, where arboricity is the minimum number of forests into which we can partition the edges of the graph. So this graph, for example, has arboricity 2, because the edges can be partitioned into the blue forest and the red forest. Arboricity is closely related to the density of the graph. In particular, if the arboricity is low, then there are no dense subgraphs in the graph, and vice versa. In fact, every subgraph on R vertices has at most alpha R edges if the arboricity of the graph is alpha. And bounded arboricity is actually a reasonable assumption for many real-life networks. For example, in social networks, there might be some dense subgraphs corresponding to friend groups and communities. However, the size of those groups is relatively small compared to the size of the entire network. So we can say that there is an upper bound on the arboricity of that graph. And also, another well-known class of graphs of low arboricity are planar graphs, which have arboricity at most 3. And let me just note that in dynamic streams, where we can both insert and delete edges, the intermediate graphs in the middle of the stream can have high arboricity. We just care that at the very end, the last graph has arboricity bounded by alpha. So these are all the results on approximating the size of maximum matching in arboricity alpha graphs. The ones in blue are the ones I'll be talking about today. So I'll be presenting an alpha plus 2 approximation using space alpha n to the 4/5, which is sublinear in the number of vertices if alpha is small enough. In 2017, Kormod et al. Presented another algorithm that returns an approximation which is linear in alpha, which uses slightly smaller space, alpha to the 10^3 times n to the 2/3. However, their algorithm has one restriction, that the number of deletions is limited to alpha n. And there's also a lower bound that says that if we want an approximation factor linear in alpha, then in dynamic streams, we basically need to use root n space. So our dynamic algorithm can also be slightly modified to be used in insert-only model with the reduction in space. So it gives us space alpha n to the 2/3. However, I'm also going to present a better algorithm for the insert-only model, which has the same approximation factor, but uses much smaller space, which is merely logarithmic. And then finally, for adjacent list streams, I'll present an alpha plus 2 approximation, which uses constant space. And here, when I talk about space, it's specified in words. So one edge or a counter can be stored in one word of space. So I'll be talking about 3 algorithms, one for each streaming model. But all 3 results have the following 2 parts. First, there is a structural result, where we would define this quantity sigma that is an alpha plus 2 approximation of the size of maximum matching in the graph. And then there is an algorithm, which is an alpha 1 plus epsilon approximation of this quantity sigma in the corresponding streaming model. And for adjacent list streams, we can actually compute it exactly. So I'll be defining these 3 quantities, sigma dynamic, sigma insert, and sigma adjacency, and then show how to compute 1 plus epsilon approximations of the first 2, and how to compute the last one exactly. So let me start with the structural results. First, let me make a few definitions. We define a set of heavy vertices which have degrees at least alpha plus 2, and heavy edges which have 2 heavy endpoints. So these are the ones in blue here at the top. And similarly, we have light vertices of degrees smaller than alpha plus 2, and light edges which have 2 light endpoints. So those are the ones in red. And so from that, we can immediately define sigma adjacency, which is just the number of light edges plus the number of heavy vertices times alpha plus 1, and minus the number of heavy edges. So to define sigma dynamic, we need to assign those weights to each edge in the graph, where the weight of the edge uv is the minimum of 1 over degree u, 1 over degree v, and 1 over alpha plus 1. So let's say this graph has arboricity alpha equal to 2. These are the degrees of all the vertices. And so these are the weights that we assign to all the edges. Note that, for example, this edge has 2 endpoints of degree 2. But since the arboricity of the graph is also 2, this last term is the minimum one, which gives us the 1/3. And then sigma dynamic is just the sum of all those weights for all the edges multiplied by alpha plus 1. So sigma dynamic and sigma adjacency are closely related, so I'm going to present them as one structural result. First, note that the size of the matching in the graph is at most the number of light edges plus the number of heavy vertices, because every edge of the matching is either light or it's incident to a heavy vertex. Then if we just expand this term and apply the property of arboricity alpha graphs, which tells us that the number of heavy edges is at most alpha times the number of heavy vertices, then we get sigma adjacency. In lemma 1, I'll show that this is at most sigma dynamic, and in lemma 2 that it's at most alpha plus 2 times the size of the matching in the graph. So that immediately gives us that both sigma adjacency and sigma dynamic are alpha plus 2 approximations of the matching. So I won't have time to give you full proofs of the lemmas, so just give you a general idea. So for lemma 1, we want to split this sum into 3, depending on what kind of edge we're dealing with, whether it's light, heavy, or neither. And then for each of those 3 cases, we can bound x sub e separately, and then do some algebra to relate that to the number of light and heavy edges and heavy vertices. In lemma 2, we first note that our assignment of weights satisfies the conditions of being a fractional matching, and the maximum weight there is at most 1 over alpha plus 1. And then we can use Edmonds' theorem to relate the size of that fractional matching to the size of maximum integral matching in the graph. So that would give us lemma 2. And finally, let me talk about sigma insert. First, we define the set E sub alpha, which is the set of edges UV, such that the number of edges incident to either U or V that appear in the rest of the stream are both at most alpha. And let me give you an example. Let's say we care about this edge E, and this is its neighborhood in the graph. The numbers correspond to the ordering of the stream, and let's say that the arboricity of the entire graph is 3. Then these 4 green edges are the ones that appear alpha E in the stream, and there are only 2 of them for each endpoint, which is smaller than alpha, and so the edge is in the set E sub alpha. However, if we just reorder the stream and move E closer to the beginning of it, now these 6 edges are the ones that appear after E in the stream. And now 4 of them are incident to this one endpoint, which is greater than alpha, and so E is not in the set E sub alpha. So as you can see, the set depends on the stream ordering. However, we can show that regardless of the ordering, the size of that set is always an alpha plus 2 approximation of the size of the matching. However, we need to do a little more work to define sigma insert. So let's say that G sub t is the graph consisting of the first t edges in the stream. And here we're dealing with an insert-only stream, so G sub t is always a subgraph of G. And we'll let E alpha t be the set E sub alpha defined on this subgraph. Applying the lemma, we know that the size of the set is an alpha plus 2 approximation of the matching in the subgraph G sub t. And finally, we define our sigma insert as the maximum over all time steps t of the size of those sets. And note that even though we only have insertions, the size of those sets can go up and down throughout the stream. So let's say that it is maximized at some time capital T. But then on the other hand, the size of the matching is a monotonic non-decreasing function of T. And so we know that sigma insert is on the one hand greater than or equal to the size of the matching. And on the other hand, it is at most alpha plus 2 times the matching in the subgraph G capital T, which is at most alpha plus 2 of the matching in the entire graph. So sigma insert is still an alpha plus 2 approximation of the matching in G. And again, I'll just give you a general idea of the proof of lemma 3. For the upper bound, we define those weights y sub e, where it's 1 over alpha plus 1, if the edge is in the set E sub alpha, and 0 otherwise. So as before, we can show that this is a fractional matching with maximum weight 1 over alpha plus 1. On the one hand, the size of that matching is exactly the size of the set E sub alpha divided by alpha plus 1. And on the other hand, we can use Edmonds' theorem to relate it to the size of maximum integral matching in the graph. So that would give us this upper bound. For the lower bound, we just want to carefully count light edges and edges that are incident to heavy vertices that belong to the set E sub alpha. And then from that, we can show that the size of the set is greater than or equal to the number of light edges plus the number of heavy vertices. And as I mentioned before, this is at least the size of the matching, because each matching edge is either light or it's incident to a heavy vertex. So now I'm going to switch to the part of my talk about the algorithms. And let's start with the most general model, the dynamic streams. Here we want to do the following two things in parallel. If the matching is small, as in smaller than n over 2/5, then we want to use a completely unrelated algorithm for matchings of bounded size, where the space used by the algorithm is quadratic on this bound on the size of the matching, so it uses n to the 4/5 space. Now, if the matching is large, we want to estimate our sigma dynamic. And we will be doing that by computing our weights x sub e for a particular set of edges that I'll define in the next slide. And note that our approximation of sigma dynamic is only going to be accurate if the size of the matching and thus the size of sigma dynamic itself in the graph are large, which is why we had to split our algorithm into two in the first place. And also note that in insert-only streams, we can use the greedy algorithm for approximating small matchings over here. And that uses linear space in the size of the matching as opposed to quadratic. So that reduces the total space to alpha n to the 2/3. So now let's see how to estimate sigma dynamic. First, we will be sampling a set of vertices T, where each vertex is included in T with probability roughly 1 over n to the 1/5. So the size of that set will be roughly n to the 4/5. And for those vertices, we will be computing the degrees. And another thing we need is a set of edges E sub T, which are the edges with both endpoints in T. And so since we know that at the end of the stream, the arboricity of the graph will be bounded by alpha, the size of that set will be at most alpha n to the 4/5. However, in the middle of the stream, the arboricity can be higher, so the size of that set can be larger. And if we don't want to use too much space, we can't just collect all the edges in a sub T throughout the stream. And what we do instead is we use sampling. And in particular, we sample the minimum of the size of the set and alpha n to the 4/5 edges in E sub T. And so this allows us to limit the number of space we're using, but at the same time, at the end of the stream, we will collect all the edges in this set. And so for our estimation of sigma dynamic, we will just use our weights x sub e on those edges in the set E sub T. And we can compute those weights because we know the degrees of vertices in T. And so I'm not going to prove that. No question?
What happens if you don't know alpha?
Well, so we're assuming that we do know alpha, or at least some upper bound on alpha. And so I'm not really sure what happens if you don't.
So I mean, this question, what happens if you think you know alpha, but the band is wrong? How do you know, it's too low. It turns out alpha is higher. What goes wrong in your algorithm?
So I would say that if our alpha is too low, that we will not be sampling enough edges, and so our estimate will be off. So we will not be getting the correct approximation factor.
Another question.
Yeah.
But are you able to detect that alpha was off after the fact?
I'm not sure.
Because if you could just like repeat it log times to test every alpha.
Yeah, but then your space will be too large. So your space depends on alpha.
Oh, right, yeah.
Yes. All right, so we use this sum as our estimate. And I'm not going to show that it is accurate. It's just standard applications of Chernoff and union bounds. So I'm going to switch to insert-only streams. And here the idea of the algorithm is that we want to keep a sample of edges in the set E alpha t at each time step t, such that on the one hand, we can get an accurate approximation of the size of that set, and on the other hand, we can use a small amount of space. So this is the algorithm that we will be using. We set our sampling probability p to be 1 in the beginning of the stream, and then as we're processing the edges, we sample each of them with probability p. If the edge is sampled, we store the edge, and we also store counters for the degrees of its endpoints in the rest of the stream. If at some point we detect that the edge is not in some set E alpha t, so one of the counters exceeded alpha, we just throw out that edge. And also, if at any point in the algorithm, the number of edges we're storing exceeds 40 epsilon to negative 2 log n, then we halve the sampling probability, and we delete every edge we're currently storing with probability 1/2. So we're basically emulating sampling with lower probability. And then at the end of the stream, we want to return the maximum over all time steps t of the number of samples we were keeping at that time t divided by the sampling probability at the same time. So now let's see why this works. Let's define k to be such that our sigma insert is sandwiched between this quantity times 2 to the k minus 1 and the same quantity times 2 to the k. And we can show that with high probability, if our sampling probability is high enough, as in it is at least 1 over 2 to the k, then we can compute accurate approximation of the sizes of our sets E alpha t for all t. And here accuracy is in terms of our sigma insert. So for the largest such set, we get 1 plus epsilon approximation of sigma insert. For smaller sets, we might not get a 1 plus alpha approximation, but we don't care about those because we just care about the maximum one. And so this just follows again from Chernoff and union bounds. And the second thing we want to show is that we do not switch to probability, which is too low, as in smaller than 1 over 2 to the k. And that happens if you actually get down to sampling probability 1 over 2 to the k, then the number of samples you're storing does not exceed 1 plus epsilon times sigma insert divided by 2 to the k, which is strictly less than 40 epsilon to the negative 2 log n, which was our cutoff to switch into lower probability. So that does not happen. And the last thing I'll be talking about are adjacency list streams. And here we actually just need the degrees of the vertices in the graph. So we treat our adjacency list stream as the degree sequence. So from that, the number of heavy vertices can be easily computed by just keeping a counter. As for these two terms, we note that if we take the sum over all heavy vertices of the degrees of those vertices, then we count each blue heavy edge twice and each gray edge once. And if we subtract that from all the edges in the graph, we get exactly the light edges minus the heavy edges, which is what we wanted to compute. And these two quantities can also be easily computed from the degree sequence by just storing a couple of counters. So this gives us a constant space algorithm. All right, so in conclusion, I just want to give a quick summary. So I talked about a few quantities that give a good approximation of the size of maximum matching if we know that the arboricity of our graph is bounded by alpha. And I also showed how those quantities can be efficiently computed in various streaming models. So there are a few questions that are still open. First of all, so far it looks like our methods only give us alpha plus 2 approximation. So a question is whether we can do better than that. And second, for dynamic streams, there's still a gap between upper and lower bounds on the space that the algorithm uses. So closing that gap would be another open question. And this is all for me. Thank you for your attention.
Thank you. Any questions? There's actually a few minutes, 5 minutes at least for questions. Yeah.
So what if you have like a setting where you can only look at some parts of the graph as pockets? and then you have to stitch the matchings across all of those. So something like a parallelization of the maximum matching algorithm. Right? Like I could also look at my stream as something that gives me a chunk of data at one point that I can store in the memory, and then I compute something, but I have to stitch that solution with the next chunk that I get in the next time.
Well, I guess in this case you can kind of view the stream as like the first part of the stream is you looking at the first chunk, the second part of the stream is you looking at the second chunk. So every time you're looking at the new chunk, you will have some summary of the ones you looked at before. So if you end up processing the entire graph in your chunks, then yes, you can see it as a stream.
I was wondering, so in your model, the space is in some sense deterministic. But can you sort of use the same results to talk about a model where maybe you take more space but amortized over, like if you have random, or if you have a random order over insertions and deletions, the amortized bound is still small. So you may take large amounts of space in some settings, but
yeah, so we haven't actually looked at random order streams for this model, so I'm not sure if that would give you any advantage. But yes, for some problems, assuming that your ordering is random does improve your algorithm.